So very pleased to welcome our next speaker, Miolane from INRIA and Stanford.
Thank you. Good morning, and thank you to the organizer for giving me the opportunity to talk at this workshop. I'm very honored to be here. I'm going to present a work on template shape estimation, how we can correct an asymptotic bias, and this is joint work with Xavier Pennec and Susan Holmes. So the basic idea here is not to introduce new differential geometry or new algorithms, but rather to use the differential geometry and the Riemannian geometry we know to evaluate an algorithm that is used in computational anatomy. And this algorithm is what's underlined here. It's called template shape estimation. So why template shape? Because in computational anatomy, when we have a database of shapes, for example, brain shapes, the first step is often to compute a prototype of these brain shapes. Prototype is the template shape that is in the middle there, prototype that best represents the population. And this is done by an estimation procedure, so that's why there is the term estimation here. So basically we assume that there is a real template shape that exists, and this real template shape we're trying to estimate. So to make this a bit more formal, but we're going to get into the details later. As I said, we assume there is a template shape T belongs to some shape space. A generative model where some randomness is introduced generates the observation that we have. And the whole goal of the algorithm is doing the reverse. So given the observations, the brain images here, can we recover the parameter that has generated them? And of course, when you compare these two, it depends on the generative model that you have assumed and the estimation procedure that you're using. But when there is a usual generative model that is assumed, and when we use the standard estimation procedure for this, so by standard I mean something that is often used in the computational anatomy literature, there has been an example where actually these two are very different. So it's a simulation that was done by Sonia Ramin and Frechet back in 2007. They took the usual generative model of the computational anatomy literature, where the template was not a 2D or 3D image, but a 1D image, so 1D signal. It was this step function that generated some observations, 1D signal observations, and then using the estimation procedure that is used in computational anatomy, even with a very high number of data, a very high number of observations, this was the estimated template with all these minima and maxima here. And this was a bit worrying for the computational anatomy literature, because if this is what we get when we're trying to estimate that, then what does this represent? If we have a lot of minima and maxima in that prototype of the brain shape, we may actually see anatomy on this brain shape that is not relevant, that not correspond to anything physical for medicine or anatomy. So the goal of this presentation is to study this bias. Why is there a bias? When does it appear? Is it important? And if we can quantify it and see that it is in fact important, can we correct it? So this is going to be the outline of the talk. First, I'm going to introduce the geometry that we'll use to characterize this phenomenon, get into details about the generative model that we assume and the estimation procedure used in computational anatomy. Then I'm going to show the existence of the asymptotic bias in that setting and also give a geometric interpretation of it. This is the main contribution of this work. And then I remember when I first presented this work, Alain Trouvé asked me if I thought that we could correct this bias, and back in the time I said, I hope. Since then we did a little bit more than that, so I'm going to present one way of correcting it. And lastly, we'll see some simulation and real data experiments. So first, the geometry, generative model, and template shape estimation, so the framework. The geometry is not very complicated. I just want to introduce the assumptions that we make to derive the geometric phenomenon of the bias. So we take an object space, also called a top space, M will be a Riemannian manifold of finite dimension, and the Riemannian distance on M will be called dm. On this Riemannian manifold, there is a Lie group G that will act on it, and we also assume that it is finite dimensional. It's acting on the left, and the action is isometric. So on here, you can see maybe one of the simplest subspace, or object space that verifies this is the space of two landmarks in R2. So if you have one landmark here and one other landmark here, and you want your Lie group G to characterize all the configurations of these two landmarks, which shapes is unchanged, you can take the group of rotation. So we're going to consider as a running example object space R2 and Lie group SO2. And in that case, the orbit of X is just a circle. Because without loss of generality, we can fix one of the landmarks at 0. We're just changing the coordinate system. So this is the object space and the assumptions for the later derivations. Under this, we can consider the corresponding shape space. So you know it's the quotient of M by the Lie group. There is a quasi-distance that is induced by the Riemannian distance. And for the example of our two landmarks, the shape of two landmarks is the distance between them. When we quotient R2 by SO2, we get R plus, and this is indeed the distance between the two landmarks that is represented by R plus. So I'm going to use this kind of drawings in all the presentation, so that's why they are here. And the further assumption is that T, so remember T is the template shape that people are trying to estimate. T is taken to be a principal shape in the sense that if you take a representative of T in the object space, then you want its isotropic group to be as small as possible. And this is not a very big assumption because you can show that the set of principal shape is dense in the shape space. But it's still an assumption we make. So this is the geometry. Now we're going to move to the generative model. So generative model, this part is a bit tricky because remember you want to estimate T, and if you change the generative model, then maybe your estimation is going to be better. But we take this generative model because this is the one that is taken in the literature. So we start with T, the template shape that we want to estimate. In the two landmarks case, it's just the distance between the two landmarks in R plus, which is the shape space. You can imagine that it's the shape of a brain. In the first step of the generative model, you pose this shape in the object space. So for the two landmarks, you just give it an orientation, which G is a rotation. In the general case, you use the isometric action of G on T. And you can imagine that you can rotate your brain shape if you wish. Here, you need to have a distribution on the Lie group. I'm not going into details here. You could take a truncated quotient or something. It doesn't really matter because the next step is adding the noise, and the noise will be isotropic in the Riemannian manifold. So in the case of the landmarks, we assume that there is noise on these landmarks. And so the configuration that you actually observe is this one, is xi. In the case of the brain images, you can imagine that there is noise that is on the image because of the measurement error. And in the general case, you use the Riemannian exponential from the point gi dot t with this vector, which is a normal. So this is how we assume the data are generated. And now we're going to see the estimation procedure that is used in computational anatomy to estimate T, the prototype of the brain shape, the prototype of the shapes in general. And the template shape estimation procedure that is used is an iterative procedure. You start with the template shape estimator to be one of the data, and then you iterate 2 states at each iteration k. In the first state, you take each object xi, and you register it to the current estimate of the template shape. So you take xi, you register it to the current estimate, so tk, of the template shape. It gives you, so it's optimization in gi, so it gives you this point, this registered point. You project it indeed in the quotient space because remember here, this is R plus. This is the quotient space as embedded in the object space. First step of the iteration. Second step, you take the average, so more precisely the Frechet sample mean in the quotient space of the registered point. So here you compute the iterated estimator tk plus 1 as the Frechet mean in the quotient space. And you do that until convergence. So I'm going to show a demo of what it does. More precisely a video of a demo, but it's online, so you can view the demo right now if you have internet. So if you put that URL here, you can try it now. This is just the example that I've used until now. If you change the template, you see that this will change. You can also choose the pose here. So as I said, because the distribution we put on the Lie group, so the rotation S2 here doesn't matter, it's just a direct here, which is in pi 0. And you can choose also the noise level. The gray dots are the observations, the black dots are the registered observation, and you can see how the estimated template is from the real template. And you can see that there is a difference, but this difference will not depend on the number of observations. Because if you put a high number of observations, there is still a difference here. And this is in a very simple case because it's 2 points in R2. You can also do it on the sphere. So you just change the URL here to sphere, and it's basically the same thing. So 2 landmarks on the sphere, and yeah, the visualization is not very good, so it takes some time. But same thing, you have 2 points on the sphere. You consider the group of rotation acting on it. You can change the template, the pose, and when you vary the noise level, you can see that there will be a difference between the template and the estimated template. So not when there is no noise, but if you change the noise level, then there is a difference.
Okay, what is the pose?
So you take the group of rotation SO2 acting on the sphere. So the orbits will be the sphere, the parallel sphere, and so the pose is the longitude in that case, if this is the North Pole. So this is the algorithmic approach that is used in the literature. What we are really going to study here is the closed form approach. So there is a link between the limit of this iterative procedure, so the template estimator that is reached by this estimating procedure, and the Frechet sample mean in the quotient space. So in this simple case, it's exactly the same. Recently, there has been work by de Villiers, Alassonnière, Trouvé, and Penney to show that this procedure, under certain assumptions, converges to a Karcher mean in the quotient space. What we are going to study as a proxy for the limit of this procedure is the Frechet sample mean in the quotient space. And more precisely, we are going to study it in the asymptotic limit on an infinite number of data. So we assume that we have an infinite number of observations, x. So I presented the geometry, the generative model that we assume, and the estimation procedure. Now I'm going to show the asymptotic bias of the template shape estimation. So why we have this difference between what we are trying to estimate and what we really are getting, even with a very high number of observations. And the main contribution of this work is really to give a geometric intuition about that, and this can be summarized in this picture. So again, using the 2 landmark example. So this is the orbit of the template shape. So template shape of the 2 landmarks is the distance between them. This is all the orbit of the template shape. When you generate your data, so you start from here, you pose it, and then you add noise. You generate another data, you pose it, you add noise. And when you do that, you see that because of the curvature of the template shapes orbit, there is a higher probability that you will generate, that the observations will be generated outside, in that case, of the template shaped orbit. And so during the estimation procedure, what happens is that when you register all the data points, when you project them in the quotient space, there will be more points on that side than points on this side. And because of that, when you compute the mean, the Frechet mean in the quotient space, there will be a bias because it will be outside, so greater in that case than the template shaped orbit. So we can say that the curvature of the template shaped orbit at the scale of sigma, which is the standard deviation of the noise, creates the bias. And we can also go a little bit further by saying that why is it that we have this curvature? Why are these orbits curved? And this is because the presence of a singularity, in the sense that here you see that you have an orbit that is only a point. This is because the isotropic group of the orbits is not the same across the orbits. And because of that, the principal orbits are curving around it. And that's why we have the bias. So if we can do the computations in the case of Rm quotiented by SOM. If we compute not only the Frechet mean in the quotient space, but all the probability distribution function of the shapes, this is what we get. And we see that when we increase, these are simulations, when we increase the standard deviation, the Frechet mean of the distribution of the projected observation in the quotient space will be more and more different of the template. And this is what we get by doing the computation in this very simple case. We can compute the bias if we set the template to be 1, so the distance between two landmarks to be 1, and dimension 3, so R3 quotiented by SO3. This is how the bias looks like. And we can compute a Taylor expansion. And what's interesting is that here we recognize the curvature of an hypersphere in Rm. So this is great, but we want a more general result than that. So since we've seen that the bias comes from the curvature of the orbits, we're going to use a general characterization of the curvature of the orbits. And we use the second derivative of the local graph at the orbit. So if we take a point at the orbit, we can compute it. We can compute the orbit as a local graph from the tangent space of the orbit to the normal space. And this includes the apparition of a tensor here, which is called the second fundamental form. It's a second derivative of this graph. And this is the leading term, is all the Taylor expansion that will arrive because of this coordinate system. The first, the zeroth order of the Taylor expansion is 0 because you go through x, and the first order is 0, 2 because you're tangent. So this is really what will lead the next Taylor expansion. If you take the trace of this tensor, you get what's called the mean curvature vector. And this is, so the first step of the results for computing the asymptotic bias. First, we're going to project all the distribution in the quotient space, and we compute the probability distribution functions of the projected object. This is what we get. So we are in the quotient space. T is the template. Z is a point in the quotient space. We are under the low noise assumption here, and this is why we do a Taylor expansion in the noise. So we've seen that the noise is responsible for the bias, so that's why we do a Taylor expansion in sigma. And what we get is this. So it's interesting because the first term will just be a Gaussian in the quotient space. I think this is Q. This is this is the quasi-distance in the quotient space. So it will be almost the Gaussian in the quotient space, but then there is some term that will change the overall shape of the probability distribution function, so that when you compute the mean, you don't get T. And in the Taylor expansion, you have different terms. The full expressions are in the corresponding paper. But what's interesting in this function is that you see two things. First, the derivative of the Riemannian tensor of M, and then the derivative of the graph G describing the orbit. and the leading term is the second fundamental form. I'm not going into the sketch of the proof. It's basically a computation. But to start the computation, you take you go in the question space, you take a ball of radius r that you fixed. You show that these terms will go exponentially to 0 in sigma, and then you do Taylor expansion in that integral, and you compute everything. Once you have that, you can compute the average. And this gives you the bias, because you can compute you sit at the real template shape t, and you compute the Riemannian logarithm of the estimated template seen at t, and this gives you the bias. So this is a vector at t. And this is what we get. So again, a Taylor expansion with respect to the noise level, and the leading term is the mean curvature vector of the template's orbit, and it's quadratic on the noise level for small noise. And the proof is, again, computation, so that's how you express the bias, and that's how you compute it, using the expression of the probability distribution function of the previous one. So, as I said, this was done for t being a principal shape, and actually if you take a singular shape, the result can be very different. For example, we can have something that is not quadratic. We can have something that is linear in sigma, so this really applies only for t principal shape. And what happens if you do it with multiple template shapes? If for example, you want to do k-means algorithm on shapes, well, this bias effect has an effect on the k-means on shapes, because when the noise level is not very high, you see that the shape clusters are still kind of separated here. But if you increase the noise level, then they start to blur one into another. So this effect makes it more and more difficult to do clustering on shape spaces. So how does this work relate to what exists in the literature? Well, first on landmarks, we had results on this template shape estimation, which in that case is the Procrustean analysis. We have to distinguish shape and form in all this literature, because shape is often referred to as the quotient by rotation, translation, and scalings, which does not apply to our case because we are isometric, but rather form is the quotient by rotations and translation. And so by having this distinction in mind, you can see these results in the literature that are related to our case. There were no asymptotic bias on the mean shape. Okay, this is not contradictory because there were the scalings there. But there was an asymptotic bias proven on the mean form here by a reductor ad absurdum proof, which was really interesting and also really early on, but didn't give a geometric interpretation that we have now. And most recently, there was a study of inconsistency effect and first correction method or adaptation method for landmarks. And now on curves, there were some results in 2011 where no asymptotic bias was seen, but in this example there wasn't really noise, so that's why they didn't see the asymptotic bias. But with noise, there was a result, a proof of asymptotic bias for curves in 2D, and this asymptotic bias was shown by being given a lower bound. So it was not 0, so that's why there was an asymptotic bias. So this is landmark, this is curve. In the general case, this is the literature is divided into two kind of research. First, the non-flat finite dimensional case that we have tackled, where T is a principal shape and the Taylor expansion is done for sigma going to 0, the noise level, standard deviation of the Gaussian noise. On infinite dimensional Hilbert spaces, a lot of work has been done as well. And not even the geometry is different, but the Taylor expansion is often done with a high noise level, so it's very complementary from our study. And also they give insights for non-isometric group action, which is different from what we've done. So now I'm going to show how we can estimate this bias, so the difference between the estimator and the parameter, and if we can quantify it, we can correct for it. Maybe first, the first way of correcting it would just have been to change the estimation procedure, because if this estimation procedure is biased, maybe we can change. And for example, Stéphanie Alassonière has suggested to use a Bayesian framework to kind of avoid this problem. But even with that line of thought of changing the estimation method, we want to know when. we should change the estimation method. So we want to know when the bias is important. I'm going to present only one method that allows to quantify and correct the bias. It's called the iterative bootstrap because it's a modification of the bootstrap technique that is very well known in the statistics community. I will not present the bootstrap because we can just look at this by itself. So this is how it goes. We assume that we know the standard deviation. If we don't know it, we could think about estimating it. This is what we want to estimate. This is our first guess. It's biased because we have computed it with the estimation procedure that I've presented. It's still the first point in our iteration. So what we do is a simulation. Since we know sigma, we generate new data around our first estimator. We generate new data, and because we have assumed we know the generative model, and since we have generated new data, from this new data we can compute the estimator of their templates. So we compute this guy, which is the estimator of this guy. And then the difference between them is an estimator of the distance between these two. So we can just take the difference between the black guy and the red guy and plug it. And this gives us the next iteration of the template shape estimator. And we do that until it converges. Does it converges? We can show that this is a fixed point algorithm, and so under a good assumption, it does converge. And this is very interesting for maybe 2 or 3 reasons. First, it allows us to compute the bias, to correct for it, but also from a more fundamental perspective, the bias was a good thing because it was an indicator of a curvature of the principal orbits. And so if we can compute the bias, then we can get insight about the curvature of these principal orbits. So imagine you're using some finite dimensional manifold with a Lie group acting on it, and you don't really know what your curvature is. You can just do a bunch of simulations, and since it will be simulation, everything will work because the generative model would be perfect. And so you could get insight about the curvature of your principal orbit.
How do you know what the sigma is then?
So yeah, I assume it is known. You could compute it, estimate it, for example, as the sigma of the probability distribution function on the quotient space.
So that might be biased.
Exactly, yeah. So then you will have to, yeah.
When it converges, you know that it converges to the bias?
Yeah. So actually the point, this one, so the estimator converts to the real parameter, and so at the end you have both, so you can compute the bias.
Yeah, but with bootstrap you have not easy because you have this double asymptotic.
Yeah, under our assumption it does converge. Yeah. But yeah, because in the limit of an infinite number of data, of simulated data, etc.
You need to have a noise which is invariant under the group action.
Yeah.
Because you
Yeah.
will be able to resimulate. No?
Yeah. So for those who know about the bootstrap, there is also a technique that's called a nested bootstrap that's also iterative, and ours is slightly different and less robust. We need a high number of observations in order for it to converge, and we also need to generate a very high number of observations every time we do the bootstrap. But it corrects perfectly if the generative model is good, and as I said, it's a computational tool to estimate an orbit's curvature. So now I'm going to show some experiments, simulated and real case experiments. So this is the 2 landmarks case that you've seen, like 200 observation, the template is 1. So yeah, this is the template. These are the registered observations. And this is the initial estimate of the template in that case. So we see it's different from what it is supposed to estimate. If we do an iterative bootstrap in less than 10 iterations, you can see that it will converge. So this was for a signal over noise ratio, T over sigma equals 1. This is just something that we define, is the distance of the template from the singularity of the shape space at the scale of the noise. If we change this signal over noise ratio to something that's a bit lower, the estimate is even worse, but then the iterative bootstrap will still converge, even with this number of data. So this was for two landmarks, shapes of two landmarks. Can we go into some things that are more interesting, maybe three landmarks? So this is the template now, the triangle. Its size is 1. We define the signal over noise ratio to be the size over sigma. It's 1 in that case. If we have this observation that are these triangles and you register them, we get this. This is the initial estimate of the template. And without correction, you can see that the error is of 10% with respect to the template size. And the iterative bootstrap allows you to correct it so that the error at the end is less than 1%. So you can see the iteration in blue, and they converge to the green one. So when is the bias important? Of course, you can use the iterative bootstrap to quantify it. But the relative bootstrap is kind of very expensive, not that much when you're dealing with 2 landmarks or 3 landmarks. Imagine doing it on images, that will be very expensive. So what you really want to know is maybe do it once and for all, understand when there is a bias, and then just use this understanding as a rule of thumb for the later case. And when you know that a bias will be important, you don't choose that method and you go to something else. In our cases, when is the bias important? Well, it's when the signal over noise ratio is close to 1, or in terms of geometry, when the distance to the singular shape over the noise is close to 1. So for the 2 landmarks example, is when this distance here is similar to the standard deviation of the Gaussian noise. And now we can go to real dataset examples. So I've shown simulation of landmarks, of set of 3 landmarks. In 2D, we can take also 3 landmarks in 3D, and then we get to something interesting. So this study was a statistical study, and they wanted to compute differences in shapes for monkeys that had healthy optic nerves and monkeys that had an optic nerve with a glaucoma. And they wanted to show that this set of 3 landmarks in that data set has a different shape from this set of 3 landmarks in this data shape. So they do a Procrustean analysis, and they try to do to find a significant difference in the template shape. So the question is, in this statistical study that was done in 2015, is there a bias? Well, we know that there is a bias, but is this bias important and important enough to have bias the result of the analysis? And so, in that case, I did a nested bootstrap, so not the iterative bootstrap that I presented, because the nested bootstrap is more robust with respect to change in the generative model. And I computed that there is in fact less than 0.02% of difference. So actually, even if we debias the thing, it doesn't change the result of the analysis. And this is because people often do maybe statistical analysis on data where the noise is not too important, because they intuitively know that if there is too much noise, maybe they will not be able to see something in their data. And so this is the last real case example that I want to talk about. So the original motivation of this work is really computational anatomy and organ shapes that are way more difficult than shapes of 2 landmarks or 3 landmarks or a big number of landmarks. So can we say something for the template shape estimation of brain? And there are a lot of complications associated to that, because the space is infinite dimensional if you take the L2 space on the image domain. And also the Lie group can be infinite dimensional because you take diffeomorphisms. And then the template shape estimation that people use has a regulation in the registration, which was not taken into account in this theoretical analysis. So a lot of complications, but we still try to take our analysis and apply it to this case. And the question we asked was, which regions of the templates are more likely to be biased? So I'm not going to go into the details here because it involves some Morse-Made complex and stuff like that, but this is what we got. So this region of the brain template were less biased, and the region here were more biased. So if we summarize, we studied template shape estimation, which is an algorithm that we didn't invent, but that has been used for more than 15 years in computational anatomy, and we asked the behavior of this algorithm. We knew that there was a bias because there were simulated examples, and we gave a geometric interpretation of this bias. So why is there a bias? When does it appear? There is a bias because of the curvature of the template-shaped orbit in the object space. So it appears as long as these orbits are curved, so when you have singularities in the shape space. How important is it? Well, we have a rule of thumb now. It's important when the signal over noise ratio is close to 1, which is when the standard deviation of the noise is kind of the same scale as the distance of the template to the singularity. Can we correct it if it's needed? So we can quantify it and correct it if it's needed using parametric bootstrap procedures. I think these procedures are maybe more useful to get an intuition about when the bias is important in your case, and then once you have this intuition, maybe you want to switch to another method, because correcting it for bias at each single case will be probably too computationally expensive. And is there an impact for computational anatomy? So what's good is that statistical studies done so far, we are usually in the regime when there is no problem, because people have the intuition that it's better to do statistics when you don't have more noise than information. But if we can correct for a bias, maybe we can go to less good regime and try to do statistics, even when the noise is important. Thank you.
Questions?
That old memories. I cannot remember that time when I was doing maximum likelihood, that it was at least known in the field that when you were using a maximum likelihood alternating with estimation of the mode, when you had the hidden data, you were biased. So this is a special case of the situation. But so I'm wondering now, I don't think there is any general study of that, but would you be able to rephrase everything in a general case of estimation under with hidden variables, and maybe use information geometry tools for this purpose, and maybe retrieve what you found?
So yes, it's very related to maximum likelihood and standard approximation with mode. So in the estimation procedure, we have these two steps. The first corresponds to the... So there is maximum likelihood to estimate a parameter. You can approximate this by using the EM algorithm. And then you can do an approximate... You can use the EM algorithm to converge to the maximum likelihood estimator, and then you can approximate the E step with the approximation with mode, which is actually exactly what we've done. I don't know how well this has been studied on manifold, but it's true that it's well known on flat manifolds, so on Euclidean spaces. Could we rephrase that using information geometry? So as far as the proofs are concerned, I use a lot the continuity of the spaces with integrals and differential geometry, and that's how I compute things. If you will have hidden variables, so in our case, the hidden variables are the element of the Lie group. If you will have hidden variables that will be different, for example, part of a finite set, I couldn't use the same proof, but we could use other two.
There's no place in your proof in which something looks like a Fisher information.
Yeah.
I think it's not easy, because it's not enough just to understand the difference between the mode and the posterior distribution. You need to have all this iteration and so on. I think in some sense this is a way in a simple case to understand, to have a more clear feeling about what's going on, because in the general situation it's, I think, quite well.
So you've made experiments with 3 points, and so you say that you can estimate the curvature or the mean curvature of something. So what are the estimation of the curvature in your experiment?
So
And how does it depend on the choice of the metric, the kernel metric?
So I didn't estimate it, but we can get quantitative sense of it, because so the bias is the difference between what you estimate and what you have. And you can compute that, and this is proportional to the curvature at the and to the square of the standard deviation. So you could just give one number, and it will give you an estimate, but it's not a vector. If you would like to get, oh no, you could also get the vector. I don't have the result, I'm just going to do it now.
The answer I was waiting for, is it positive or negative, and when is it positive or negative?
Oh, okay. I don't know. I'll have to, so if you go,
Yeah, here.
yeah. So we'll have to take the limit, well, yeah. I mean, in that case, when you simulate, actually you know the true and you know the first one, so you know the bias. So you'll have to compute the logarithm of the estimate with respect to that point in the quotient space. It will give you a vector, then divide, and then the direction of this vector will give you the sign of the curvature.
Any more questions? It's coffee time now, I think, anyway, so let's thank Nina again.